Our universe's age has been a subject of intense interest and debate for centuries among scientists. Although at first it appeared to be a straightforward question, the quest for an answer has demonstrated to be much more involved than anticipated. This query persists today, continues to bring about debate as fresh research consistently challenges our current knowledge of the universe's age and the infinite galaxies. Just last week, a groundbreaking research study using data from the introduction of the James Webb Space Telescope posed a bold challenge to the long-standing consensus that the universe is circa 13.8 billion years old. The universe, according to this new study, could be twice as old as previously thought, potentially overturning the currently available cosmological model and solutions to the mysteries of the past encompassing the initial galaxies. But is this really attainable? Let us explore this theory as we begin to explore the vastness of the cosmos and analyze this fascinating discovery. If you intend to remain informed of the most recent developments in the universe and beyond, don't forget to like this video, subscribe to our channel, promote it by sharing it, and make use of the notification bell. It's crucial to recognize that one of the most insightful pieces of information we have about the universe's age is 13.8 billion years. However, this figure is now being reassessed due to the recent surge of exciting new research. By traveling back, we can eventually discover that the early universe was vastly different from what we observe today. The galaxies and stars we see now formed through the gravitational merging of objects that consisted of younger, more pristine stars. In the very beginning of the universe, neither stars nor galaxies existed. If we continue to look in reverse, we eventually arrive at the Big Bang, which marks the origin of the universe as we understand it today. At the moment, astronomers and astrophysicists studying the universe's origins claim to have calculated its age with an impressive margin of error of less than 1%, a remarkable achievement that allowed us to pinpoint the universe's birth date. There are two primary methods for determining the size of the universe's age, and both are in agreement with the current amount. The first approach follows the universe's history, a potent approach for estimating its age. This technique was possible because of the discovery of the expansion of the universe in the 1920s. In physics, if you understand the system's control equations and you can observe how it develops over time, either forward or backward, so long as the system's and physical laws' composition remain unchanged. In the laws of cosmology and astrophysics, governing the universe's expansion are derived from solving the theory of general relativity in the context of a universe that, on average, is uniformly filled with matter in all directions. This is referred to as a homogeneous and isotropic universe. The outcomes of the solution are known as the Friedmann equations, named after Alexander Friedmann, who came up with them first in 1922. These equations describe how a universe filled with matter must expand or contract in a specific manner. The rate of expansion or contraction changes over time depending on two factors. First, the present rate of expansion at any given point, and second, the type of existent universe-wide content at that instant. Early on in the history of scientists, they used to joke about cosmology that it was about finding two important numbers. These two numbers would provide all of the information necessary for comprehending the universe's evolution. The Hubble constant that tracks the current expansion rate and the deceleration parameter, which measures how much the rate of expansion changes over time. What we now know is that the universe is not slower than previously thought, but is actually expanding at a faster rate. If we could precisely determine the universe's expansion rate, we would gain a deeper comprehension of the structure of the cosmos, including ordinary matter, dark matter, radiation, neutrinos, dark energy, in addition to other parts. Additionally, we could trace the universe's beginnings with the Big Bang when it was hot, dense, and contained within a restricted volume. The length of time to reach that point in the past helps us determine the universe's age. The study, published on July 7th in the monthly notices of the Royal Astronomical Society, casts doubt on previous estimates of the universe's age, suggesting they may have been extremely inaccurate. This new research tackles the impossible problem of the first galaxies, which has perplexed scientists for a long time. As stated by the findings, certain galaxies thought to have formed shortly after the Big Bang could actually be much older than previously assumed. Observations revealed by the James Webb Space Telescope that some galaxies, like Methuselah, exhibit a maturity and mass level that would typically be associated with billions of years of development. It comes as a surprise discovery, especially considering that these galaxies were believed to have formed over several 100 million years after the Big Bang. An associate professor of physics at the University of Ottawa has suggested that these surprising observations can be explained by considering the possibility that the universe is much older than initially thought. His study presents a new model that extends the timetable for the formation of galaxies by several billion years, leading one to believe the universe could be 26.7 billion years old, twice as old as most accepted right now. This new model incorporates the worn-out light of Fritz Zwicky's theory, proposing that the observed redshift in light from galaxies far away is caused by a steady decline in energy as light travels vast cosmic distances. According to this theory, light becomes tired or weaker over long stretches of space. This contrasts with the prevalent theory that assigns the redshift primarily to moving galaxies away from us as a result of the growth of the universe. The tired light theory has sparked a lot of controversy inside the community of scientists as astronomers debate whether the loss of energy over such distances could cause not only redshift, but also a decrease in the brightness and intensity of light. Critics argue that if this were true, distant objects would appear much dimmer than what is actually observed. Furthermore, Zwicky's theory, which was first proposed in the mid-20th century, conflicted with the discovery of the cosmic microwave background radiation that can be seen all over the sky that denotes the remaining energy of the Big Bang. The resulting radiation provides compelling evidence supporting the theory of the expanding universe. Although Zwicky's theory initially seemed a contradiction, to these observations, a fresh viewpoint has been offered. Allowing the dated theory of light to coexist with the universe's expansion model, in accordance with this new interpretation, the redshift phenomenon can be understood as a hybrid effect, combining the two: expansion of the universe and the best steady depletion of light's energy during its journey through space. This updated interpretation not only reintroduces the old light theory, but also encompasses the idea of blocking constants, a basic idea that was proposed by Paul Dirac, a physicist. These stalemates, governing physical parameters theory, and interactions between particles, posit that they may have changed over time. By considering the evolution of these constants that prevent movement, the timeline for the new model, is extended. The formation of the first galaxies, observed by the James Webb Space Telescope, rather than forming only a few 100 million years after the Big Bang, could have formed over several billion years, offering a great deal more plausible explanation for their size and mass. This model also challenges the traditional understanding of the cosmological constant that is generally accepted to account for the dark energy in charge of the universe's accelerating expansion. Instead, the model suggests a modified version of the constant that accounts for the potential changes in blocking constants over time. This modification in the cosmological model could provide answers to the puzzle of the small size of galaxies found in the beginning of the universe, ultimately providing a clearer and more accurate depiction of cosmic evolution. What are your thoughts? Have we been mistaken about how much time? Share your thoughts in the comments section. If you liked it, please remember to like the video and subscribe to the channel so you don't miss out on future content like this. Thank you for watching, and I hope to see you in the next. The research's findings are not only groundbreaking, but also demonstrate a fundamental shift in the way we think about the early universe and its evolution. If this new model is true, it could alter our understanding of everything from galaxy formation to the very structure of space-time as a whole. Such a radical shift has the potential to pose a threat to assumptions that we have held for decades regarding the timeline of the universe. Researchers have long held the belief that the formation of the first galaxies occurred relatively soon after the Big Bang, within a few 100 million years. However, the new evidence from the James Webb Space Telescope is forcing us to reconsider this timeline. The notion that galaxies such as Methuselah could have formed much earlier suggests that we might have to rethink the very nature of the Big Bang itself. Might the universe be older than we thought? And if so, how would this impact our comprehension of additional cosmic events, such as the formation of stars and black holes? At the heart of this debate is the difficulty of bringing the various theories made with the intention of explaining the age of the universe together. The accepted theory, which suggests that it is about 13.8 billion years old, is backed up by a wealth of evidence, which includes cosmic background radiation from microwaves and the observed redshift of distant galaxies. Most of these observations have led scientists to accept the current model. But the new study forces us to confront the potential for this model to be incomplete. One of the most intriguing aspects of this new research is the role in proving the tired light theory, the occurrence of the redshift. When the redshift observed in faraway galaxies is due not only to the expansion of the universe, but also to the gradual loss of energy as light travels vast distances, it could offer a new perspective on how we perceive energy and light in the cosmos. This theory, while controversial, opens a doorway to new cosmological possibilities that could have profound implications for how we investigate far-off objects in space. The proposed modifications to the cosmological constant are also worth noting. By implying that the constant may evolve over time, the new model shatters the prevailing belief that dark energy remains constant throughout the entire universe's history. This concept could lead to a deeper understanding of dark energy and its role in the accelerating expansion of the universe. It also has the potential to provide solutions to some of the lingering mysteries surrounding the formation of galaxies, especially those with small sizes seen in the earliest galaxies. As the scientific community continues to digest these findings, it's clear that we are on the verge of a significant shift in our comprehension of the universe. Whether this new model will be widely accepted remains to be seen, but it's a reminder of the constantly changing nature of science. Our comprehension of the universe is constantly being refined as new data emerges. And this is a perfect example of how research can challenge established concepts and make room for new avenues of investigation. As we proceed to investigate the cosmos, one thing is certain: the quest to understand its age and origins will continue to captivate and have a lasting impact on scientists to come. Whether the universe is 13.8 billion years old or twice as old, the mystery of its formation and evolution continues to rank among the most profound questions in science. The findings from the James Webb Space Telescope have only merely skimmed the surface. And as more information becomes available, we may uncover even more shocking details about the true age of the universe and the forces that formed it. So what should we do next? New instruments and technology, like the James Webb Space Telescope, are now able to explore deeper into space than ever before. These developments will enable us to collect more precise data and refine our models of the universe's history. The questions regarding the age of the universe, its early days, and the formation of galaxies are far from settled. But with each new finding, we get closer to unraveling the mysteries of the cosmos. As we await further research and insights, it is essential to keep in mind that science is an ongoing process of learning. What we currently know is based on the best available evidence. However, it is always subject to change as we uncover more information. The possibility that the universe could be significantly older than previously thought is an exciting possibility that could change our perspective on our place in the cosmos. So, stay tuned as we continue to investigate these and other questions. The universe is vast, and we have just begun to scratch the surface. Who can say what thrilling discoveries are yet to come? As always, we'll be here to keep you abreast of the most recent developments in the cosmological world. Until then, keep pondering and remain inquisitive.